In this video, we solve problem 3.5.8 from Nagle's Fundamentals of Differential Equations, 7th edition. We're told that a 10 to the negative 7 farad capacitor, that's a 100 nanofarad capacitor, is charged to 50 volts and then disconnected. Then we're told that one can model the charge leakage of the capacitor with an RC circuit with no voltage source, and the resistance of the air between the capacitor plates. On a cold, dry day, the resistance of the air gap is 5 times 10 to the 13th ohms. On a humid day, the resistance is 8 times 10 to the 6 ohms. Then the question says, how long will it take the capacitor voltage to dissipate to half its original value on each day? Well, in order to do this, we need to draw an RC circuit. So let's say we have got some battery over here, some voltage source. And then we have a resistor. And then over here we have a capacitor. Well, we know from Kirchhoff's laws that the voltage source, we're thinking of that as adding voltage or potential energy to the circuit. That's going to equal the voltage drop for the resistor plus the voltage drop for the capacitor. But then they're saying in this situation, because we have charged the capacitor to 50 volts and then disconnected it, we can think of this situation as being like this, but with no voltage source. So E of t would be 0. And a resistance that is based on the air between the capacitor plates. And then that resistance changes. When it's a dry day, we've got this resistance. And when it's a humid day, we have a resistance that looks like this. So we can use those as our resistance in this formula over here. The voltage drop for any resistor is given by the current times the resistance, the current passing through the resistor times the resistance. And the voltage drop for a capacitor is 1 over C, where C is the capacitance of the capacitor, times the charge, the charge on the capacitor. Now, another thing that we have to remember is that current is change in charge per unit time. So this I can be replaced by dq dt. So we have 0 equals dq dt times r plus 1 over c times q. And c is a constant. In this case, our capacitance is 10 to the negative 7 farads. And the resistance actually changes. For a dry day, our resistance is 5 times 10 to the 13 ohms. And for the humid day, the resistance is 8 times 10 to the 6 ohms. And we are told that the capacitor is initially charged to 50 volts. Okay. So that's telling us, this piece is telling us that the voltage drop for that capacitor is 1 over C times Q, which is equal to 50 at time t equals 0. So if the capacitance is 10 to the negative 7 farads, then charge at time t equals 0 on the capacitor is 50 times, multiply both sides by the reciprocal of that, 10 to the negative 7 farads. And when we multiply those together, that's going to give us a charge at time t. Okay, or at time t equals 0, excuse me. So if we have this differential equation, it's actually pretty easy to solve. And we can solve it for the charge on the capacitor as a function of time. And then once we know the charge on the capacitor as a function of time, then we can use that to answer these questions. How long will it take the capacitor voltage to dissipate to half its original value on each day? And this will be half that value when V is equal to 20, or the voltage drop across the capacitor is 25 volts instead of 50 volts. What I would recommend you do in this case is just leave this as a function, or solve this in terms of the resistance R, and then substitute these two values for R so that you can answer the first part and the second part. The first part asks us, or states the answer like this. It says, on a dry day, it will take blank seconds. And if you look at the problem statement, it says use scientific notation and round to 3 decimal places as necessary. So we're going to solve this we're going to answer the question for the amount of time that it would take for the capacitor voltage to dissipate to 25 volts. We're going to do that twice, for this resistance for a dry day and this resistance for a humid day. So let's solve for Q in terms of R and then substitute whichever R is appropriate. C, that's the capacitance. We can substitute that in because we're going to have the same capacitance either way. And 1 over 10 to the negative 7th is 10 to the positive 7th. This is separable. Oh, wait, no. Well, actually, yes, it is. If we subtract this from both sides, or alternatively, subtract this from both sides and then flip the sides, we'll have dq dt times R equals negative 10 to the 7th times Q. And R is just a constant. You can keep that on either side. Either one is fine. I'd probably move that R over here by dividing both sides by R. And then in order to get the Q over here on this side, I'll divide both sides by Q as well, or multiply by 1 over Q, same thing. So the Q's reduce, the R's reduce. And if we multiply both sides by dt, we get this. So I have 1 over Q times dq is equal to negative 10 to the 7th over R times dt. Anti-differentiate each side with respect to the variable on that side. We'll have natural log of the absolute value of Q is equal to this. Now that's constant with respect to t. So you're just going to have that constant times t plus a constant of integration. And then we will raise both sides, or we'll exponentiate both sides so that e and the logarithm can undo each other. Then we'll have Q of t on this side. It's actually the absolute value of that, so it's going to be plus or minus this value over here. And this is a sum of expressions in the exponent. So we can write this as e to this power times e to that power. I'm writing it in the reverse order. And then this is just a different constant. Okay, that is the charge on the capacitor at time t, given our situation, but it does not take into account that this was the initial charge on the capacitor. So we can use this to find the value of C1. We know that when t equals 0, the charge on the capacitor is 50 times 10 to the negative 7. And we will use that here to solve for C1. Well, e to the 0 is just 1, so q of 0 is just C1. So we're going to set that equal to 50 times 10 to the negative 7. And then we would solve for C1, but obviously if this equation's pretty simple, it's already telling us what C1 is. We can use that to find Q of t. So Q of t is equal to this 50 times 10 to the negative 7th times e to this power. And if you're like me and you don't like that that is just a 50, you might want to write that as 5.0 times 10 to the first times 10 to the negative 7th. And then you've got two exponential expressions with the same base, so that's actually 5.0 times 10 to the negative 6. Okay, so that's our Q of t. That's our charge on the capacitor. And then the question said, on a dry day, well, actually it said, how long will it take the capacitor voltage to dissipate to half its original value on each day? First the dry day, and then for the humid day. Well, I will have this as my Q of t on either day, and then we will just substitute that into this equation. 1 over C times the charge is equal to the voltage, but instead of having a voltage equal to 50, we'll have a voltage equal to 25. So we'll have 1 over C times Q of t equals 25. And that's 1 over 10 to the negative 7. And if you want, you can multiply both sides by 10 to the negative 7. That will get rid of that fraction. You'll have that. And we want to solve this for R. Oh, wait, I'm sorry, not R, T. Now at this point, you could substitute in the two values for R. You could substitute in the first value of R and then substitute in the second value of R. What I would recommend you do though instead is just solve this for T in terms of R and then substitute your R values into your answer. So the first thing that we'll do is we'll divide both sides by 5 times 10 to the negative 6 to isolate the exponential. And so I'll have e to this power equals this. So you have 25 times 1 over 10 to the 7th time divided by 5 times 1 over 10 to the 6th. You can multiply the numerator and denominator by 10 to the 6th. What you would get is this. 25 times 1 over 10, or 10 to the negative 1, divided by 5. So you have 5 times 10 to the negative 1. And in order to get rid of this exponential, we'll take the logarithm of both sides. Those two functions undo each other, and we just end up with negative 10 to the 7th over r times t equals the log of 0.5. And if we're trying to get t by itself, we can multiply both sides by the reciprocal of this expression. So we'll multiply by r over negative 10 to the 7th. And that will give us 2 times. For each value of r, we'll have a different time. So on the dry day, the resistance was 5 times 10 to the 13th ohms. So we'll have t equals 5 times 10 to the 13th times log of 0.5 divided by negative 10 to the 7th. And of course, you've got 10 to the 13th over 10 to the 7th. So you can just subtract those exponents. So this is going to be negative 5 times 10 to the 13 minus 7, which is 6, times natural log of 0.5. And let's see, that's a lot of seconds. So I've got 3,465,735.903 seconds. But I'm sure we want to round. Let me look at that problem statement online again. They want us to use 3 decimal places as needed and scientific notation. So we'll say this is approximately 3.466 times 10 to the 1, 2, 3, 4, 5, 6 power seconds. And then the other one will be very similar. We'll just substitute in the resistance for the humid day. Okay, so we're going to substitute the other R value here. On a humid day, the resistance is 8 times 10 to the 6 ohms. So T is R, which is 8 times 10 to the 6 times natural log of 0.5 divided by negative 10 to the 7th. So we have negative 8 times 10 to the negative first. 6 minus 7 is negative 1 times natural log of 0.5. And we get approximately 0.5552, which in scientific notation is 5.552 times 10 to the negative 1. And these times are in seconds.